So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, welcoming you all to a very crazy integral solving video by me. I hope you can see in front of you all this Ahmed's integral. Well, this is one of those kind of integrals which are extremely tough to evaluate at first. Let me take some more integrals like that. First one could be the Gaussian integral, the classic integral, and that says integral from negative infinity to the positive infinity of e to the negative x squared dx evaluates to square root of pi. And the second one could be, although I haven't made a video on Gaussian integral, but the I have made a video on the second one, that is the Dirichlet integral. So you can just check that out if you want. Integral from negative infinity to the positive infinity of sine x over x dx, and that evaluates to pi. So yeah, like if you want, well, I'm thinking to just make some videos on the Gaussian integral, where there are multiple ways by which we can evaluate this integral. But yeah, I will bring couple of videos on that. But if you want a Dirichlet integral, so I have made a video on that. If you want, please check that out. Okay, so now I think we should begin with the Ahmed's integral, right? And this is really difficult to evaluate. It needs a lot of things. So yeah, because you can see that you are having integral and arctangent, and the argument is nested with a radical, and inside the radical you are having 2 plus x square, and yeah, all these stuffs are being like nested over there. So yeah, I think we should begin solving. We should begin like proving this, or maybe solving, evaluating this. Okay, so firstly we will assume that our integral is I. Already I did that, you can see here. So I'm just going to use the Feynman technique, that is parameterization, instead of anything else. So I'm just going to parameterize an integral I of a as integral from 0 to 1 of arctangent of a times square root of 2 plus x square over 1 plus x square and times square root of 2 plus x square dx. So this is a parameterization, right? This is where a is a parameter. And okay, so now most of you will think that like I'm going to just take the derivative with respect to a, both the sides, but this is not the first step that we are going to do. But instead we are going to evaluate for I of infinity. Just put a equals infinity both the sides. So arctangent, this becomes a times infinity times anything is just infinity, right? Okay, over 1 plus x square times square root of 2 plus x square dx. Okay, so you might have an idea about what's arctangent of infinity, that is pi over 2. So yeah, let's just replace it with that. So I of infinity becomes pi over 2 times the integral from 0 to 1 of dx over 1 plus x square and times square root x square plus 2. Yeah, okay, now we are just going to place something on the numerator here, and what we are going to do is we are just going to create something to simplify it further. So I'm just going to x square plus 2 minus x square. And now you would ask, if I have, like, on the numerator we are having 2, like after solving of everything, so I have to neutralize that with dividing 2 in this integral. So I'm just going to neutralize it with 2 plus 2x square, right? I hope you noticed that. So like I have multiplied 2 with this parenthesis, right? Okay, so this is what we are having right now. And now what I'm going to do is I of infinity is pi over 2 integral from 0 to 1. Okay, so I'm just going to, or maybe I should just parenthesize this for like easy well, yeah, it's easy to just use that, it's nothing changed yet. Okay, so I'm just going to write that again, minus x square over 2 plus 2x square and times square root of x square plus 2, and I'm just going to divide with square root of x square plus 2, and then multiply with and then divide with x square plus 2. Okay, and yeah, then we are having I of infinity pi over 2 integral from 0 to 1. Like when you just multiply this with this parenthesis, so you are gonna have square root of x square plus 2 only, and when you do this with this one, so that's gonna give us minus x square times x square plus 2 whole to the negative 1 half over, and when you do that with yeah, okay, let me tell you, this thing is being multiplied to each other, so we don't have to just divide it with twice here, right? So eventually we're gonna have 2 plus 2x square over square root of x square plus 2 and times square root of x square plus 2. Now you would ask me, why didn't we cancel this with that? So we don't need to do that, because in order to find something, right, in order to find something, you will get to know why we cannot do that. Instead, we are going to do something better. I of infinity equals pi over 2 integral from 0 to 1 um, square root of x square plus 2 minus I can write this one, like I can write this thing as x over 2 times 1, oh sorry, x square plus 2 whole to the negative half and then 2x. I can write this like that, because eventually that's gonna give us the same that we had earlier. And here, and in the denominator, I'm just going to multiply with the square root of x square plus 2 and divide with x square plus 2. So that's ultimately we will be gonna have 2 plus 2x square over x square plus 2 and times x square plus 2, right? Yeah, okay, so yeah, that's good. Okay, or maybe I should write this down as square. Oh, let me just write down it perfectly. So yeah, x square root of x square plus 2 whole square, right? Okay, and now next what we are going to do is we are just going to take pi over 2 integral from 0 to 1. So x square plus 2 minus x over 2 x square plus 2 whole to the negative half and then 2x dx over, I can write down this as x square plus 2 whole square, right? I can do that, and with division this thing comes out. Okay, so and when you just do that, so I can write down that as 2 plus x square plus x square, right? I can just open 2x square as x square plus x square, right? So that's ultimately gonna give us in the next and final step here, I of infinity equals pi over 2 integral from 0 to 1 of square root of x square plus 2 minus x over 2 x square plus 2 whole to the negative half dx, 2x dx over, sorry, and then over square root of x square plus 2 whole square over when you just solve this, so that's gonna give us 1 plus x square over x square plus 2. So this is what we are having finally right now. I know this looks ridiculously like disgusting, but believe me, that's gonna makes our life easier. Don't worry. So now our next step is let t equals x over square root of x square plus 2. And if we talk about the limits, when you plug x equals 1, so that's gonna give us 1 comes out to be 1 over square root of 3, and 0 comes out to be 0. Okay, and when you take the derivative both sides, so dt comes out to be, you have to use the quotient rule here. And if you don't know what's the quotient rule, let me just tell you right over here, don't worry. So the quotient rule is you have to take the derivative of f of x over g of x. So f dash x g of x minus f of x g dash x over g of x whole squared. So this is your quotient rule, and we are going to use that over here. So for our case, f of x is x and g of x is square root of x square plus 2, as you can see here. So let's just put all the stuffs like on here and here. So yeah, so that's gonna give us the derivative of x is just 1, so we're gonna have square root of x square plus 2 minus f of x, that is x. And when you take the derivative of this one, I'm sorry, this one, right? So that's gonna give us 1 over 2 and x square plus 2 whole to the negative half, and with the chain rule, that's 2x over the square of this denominator, right? So that's gonna give us square root of x square plus 2 whole squared. And if you can notice till now, so this is our dx, exactly the same. How amazing is that, guys? So now we're just going to play with our I infinity. So I of infinity comes out to be pi over 2 integral from 0 to 1 over square root of 3, and that's gonna give us dt over this is just t squared. When you just square this, so that's gonna give us x squared, and this becomes square, so that's eventually t squared, right? So it's 1 plus t squared, and this is just a basic integral pi over 2 arc tangent of t evaluated from 0 to 1 over square root of 3. So that's gonna give us I of infinity is pi over 2 arc tangent of 1 over square root of 3 and minus arc tangent of 0, and that's finally evaluates to pi over 2 times pi over 6, right? And that is pi squared over 12. So the work we did for I infinity evaluates to pi squared over 12. And now you would ask, what's the purpose of doing this? I would say just be patient, you will get to know what's the purpose of evaluating this one. Okay, so this much work we did for I infinity, and now we are heading towards our parameterized integral to take the derivative both sides using Feynman technique. So we had parameterized I of a equals integral from 0 to 1, wait a second, yeah, of arc tangent of a times square root of wait a second, sorry, 2 plus x square over 1 plus x square and square root of x square plus 2 dx. Now we are just going to take the derivative with respect to a both sides. So taking the derivative, something like this, integral from 0 to 1 arc tangent of a times square root of 2 plus x square over 1 plus x square times square root of x square plus 2 dx. So this becomes I prime of a, and this becomes integral from 0 to 1 taking partial derivative with respect to a of the integrand, that is 2 plus x square over 1 plus x square times square root of x square plus 2 dx. Okay, so if we take the derivative with respect to a, like partial derivative with respect to a of this integrand, so you're gonna have like you have to take the derivative of arc tangent. So let me tell you, the derivative of arc tangent x is 1 over 1 plus x square, right? So that's what we are going to do. And we have to suppose that this thing is a constant, because we are going to take the derivative with respect to a, not with x. So all the things would be treated as a constant, right? So let's take the derivative. So if you take the derivative with respect to a here, so you're gonna have I prime of a equals integral from 0 to 1. Firstly, with the chain rule, you can say the derivative of a is 1. So you're gonna have square root of 2 plus x square on the numerator, and with division you're gonna have the derivative of arc tangent of a times square root of 2 plus x square. So that's gonna give us 1 plus a square times 2 plus x square. Eventually you have to square that, right? And we were having 1 plus x square and times square root of 2 plus x square earlier dx. Okay, and now you can see that this thing and this thing getting cancelled out with each other successfully, and our I comes out to be I of I prime comes out to be I prime of a comes out to be integral from 0 to 1 of dx over 1 plus x square and times 1 plus a squared 2 plus x square dx. Okay, I hope till now everything is going correctly. And okay, now we are going to manipulate here. So I prime of a is 1 over a square plus 1 integral from 0 to 1. So to neutralize this, we have to multiply here with that only, and 1 plus x square times 1 plus a square 2 plus x square, right? And now we have to do something here that I know that's very much like, it's not good, but we have to do that. I'm sorry about that. So what we are going to do here is integral from 0 to 1. We are going to write this one with some nasty looking things like 1 plus 2a squared plus a squared x squared minus a squared x squared. And if you solve this thoroughly, so you're gonna have the same result that we had earlier here, because if you see this thing and this thing getting cancelled out, and 2a square minus a square is just a square and plus 1, so plus 1, right? Okay, and over 1 plus x square times 1 plus a squared 2 plus x squared dx. Okay, so why we did that? We did that in order to get something beautiful, obviously. Now it looks very what do you call, disgusting, but believe me, that's gonna give us something better. So I'm just going to take this much part as a different part, as a separate part. So that's gonna give us 1 plus 2a square plus a squared x squared over 1 plus x squared 1 plus this. If you if you open this up, so you're gonna have 2a square plus a squared x squared dx, not dx actually. And if you take if I'm talking about this part, so if you take negative a squared common, so that's gonna give us 1 plus x square over 1 plus x squared and times this big looking thing 1 plus a squared 2 plus x squared and dx. Okay, so from here we can say that this thing and this thing getting cancelled out, and this one getting cancelled out successfully. So eventually we're gonna have I prime of a equals 1 over a square plus 1 integral from 0 to 1 of 1 over 1 plus x squared minus a squared over 1 plus a squared 2 plus x squared and dx. Okay, so now it looks quite good because we were having a lot of troubles like here. Okay, and now again we are going to do something here. I prime of a equals 1 over a square plus 1 integral from 0 to 1. We don't have to disturb this one because this is already very easy to evaluate. It's just arctangent of x, but we are looking for this one. So it's minus a squared over 1 plus 2a square plus a squared x squared. Okay, and then the next step would be this is I prime of a equals 1 over a square plus 1 integral from 0 to 1 over 1 plus x square minus a squared over, I can write this down as square root of 1 plus 2a square whole squared and plus ax whole squared, right? I can do that. And now if you look closely, so it's a constant and x times a constant is being multiplied here. So in both the cases we are having like in this case and in this case we are having a tangent thing. So finally if we integrate that, so we are having a square plus 1 and times when you integrate this, so that's gonna give us arctangent of x only, and minus if you integrate this big thing, this big chunk of things, so that's gonna give us a over square root of 1 plus 2x squared. I'm sorry 2a squared and times arctangent of ax over, you have to just do it by yourself actually, 1 plus 2a squared, because if you do this for yours by yours, so that's gonna give you an idea about how differentiation works. Oh sorry, how integral works. Okay, so after just plugging all the like limits, so you're gonna have I prime of a equals 1 over a square plus 1 times pi over 4 minus a over square root of 1 plus 2a squared arctangent of a over square root of 1 plus 2a squared, because like when you plug 0 in both the cases it's gonna be 0 only, so we are not considering that one. Okay, and now this is our I prime of a, and this is the final result that we are dealing with, right? So this is the final step for I prime of a, and now our next step to get I of a in order to get our integral. So integrating now, integrate both sides from 1 to infinity, with respect to a only. So this says integral from 1 to infinity of I prime of a dA equals integral 1 over a square plus 1 times pi over 4 minus a over square root of 1 plus 2a squared arctangent of a over square root of 1 plus 2a squared dA. So yeah, we have to integrate this big chunk of thing, and when you integrate this thing, so that's finally gonna give us I of infinity, and that is why we did evaluate I of infinity at first, minus I of 1, that 1 to infinity, right? So yeah, we are just going to break here two integrals apart, so that's gonna give us pi over 4 integral from 1 to infinity of 1 over a square plus 1 dA, and minus integral from 1 to infinity of a over square root of 1 plus 2a squared arc tangent of a over square root of 1 plus 2a squared and dA. Okay, and yeah, that's good. Oh, did I miss something? Oh, I'm sorry. Here it was um, oh, I'm sorry, it was a square plus 1. Oh, I'm sorry about that. So from our consideration, like from our parameterization, I of 1 was when you plug 1 over here. Oh, let's don't disturb 1, I think, because that's gonna just mess up our stuffs. But and don't disturb I of infinity even. Let's just walk with this away till the very end. So pi over 4 times arc tangent of a when you integrate that from 1 to infinity, and minus integral from 1 to infinity of a over, so yeah, a over wait a second, oh yeah, or let me just write this down as 1 plus 1 over 1 plus a squared and times a over square root of 1 plus 2a squared arc tangent of a over square root of 1 plus 2a squared dA. Okay, so yeah, okay, so if we just take if we talk about this one, let's just solve it here. So arc tangent of infinity minus arc tangent of 1, that is pi over 2 minus pi over 4, that's gonna give us eventually pi over 4 only, right? So multiplying this pi over 4 with this one, that's gonna give us pi squared over 16. Oh, I'm sorry, I just erased 4 over here. So our I of infinity minus I of 1 is pi squared over 16, and minus integral from 1 to infinity of 1 over a square plus 1 and times a over square root of 1 plus 2a squared arc tangent of a over square root of 1 plus 2a squared dA. Yeah, so far so good, I think. Okay, and now we are just going to use some u substitution. So let a is 1 over u, that says dA comes out to be minus 1 over u squared, and limits would be changed as follows. When you plug a equals infinity, so that's gonna give us infinity becomes 0 and 1 becomes 1. So that's finally comes out to be I of infinity minus I of 1 equals pi squared over 16 minus integral from 1 to 0 of 1 over u square plus 1 times a was 1 over u over square root of 1 plus 2 over u squared arc tangent of 1 over u over square root of 1 plus 2 over u squared, and it's minus 1 over u squared du, right? And you know what, this minus is gonna help us to change the limits, like to change the limits in between them, like to just flip it. Pi squared over 16 minus integral from 0 to 1, and this becomes u squared over 1 plus u squared, right? And times that comes out to be 1 over the square root of u square plus 2, right? Yeah, and arc tangent that comes out to be 1 over square root of u square plus 2, and 1 over u squared du, and this u square and this u square getting cancelled out successfully. So finally we are having I of infinity minus I of 1 equals pi squared over 16 minus integral from 0 to 1, and 1 over, oh I'm sorry, 1 over u square plus 1 times 1 over square root of 2 plus u squared, as we had earlier. Oh wait a second, okay, yeah, and then this comes out to be wait a second, yeah, so this comes out to be arctangent of 1 over square root of u square plus 2 du. And now I would like to tell you something here. We know that arctangent of u plus arctangent of 1 over u is pi over 2. So from here we can say that arctangent of 1 over u is pi over 2 minus arctangent of u, right? So this is one of properties of like tangent inverse of arc, right? So we are just going to use that over here in order to get something better. Just wait for the moment, don't worry. So I of infinity minus I of 1 equals pi squared over 16 minus integral from 0 to 1, and pi over 2 minus arctangent of it's since it's a definite integral, so I'm just going to replace it with maybe x only. We can replace it with that. So arctangent of square root of x square plus 2 over and over x square plus 1 and times square root of 2 plus x square dx. I can do that. It's yeah, you don't need to worry about that. Okay, and now I'm just going to break into integrals apart this function. So yeah, that's gonna give us I of infinity minus I of 1 pi squared over 16 minus pi over 2 integral dx over x square plus 1 and times square root of x square plus 2 and minus integral from 0 to 1 of arctangent of x square, oh I'm sorry, a radical square root of x square plus 2 over x square plus 1 and times square root of 2 plus x squared dx. If I'm talking about this thing, what's that? Do you remember, guys? This is what we had. This is, so yeah, this is our I, this is our target integral I. So I'm just going to replace it with that, right? How amazing is that, guys? After solving that, we are just getting over there only. Or maybe, oh, I'm not talking about I, but I'm talking about I of 1, because eventually that's just I of 1 only. When you just replace like when you just plug here 1, so that's gonna give us our I. So let's just write that down with I of 1, right? And if we talk about I of infinity, so wait a second, okay, I would like to just I would like you to note this point down here also. This is our I of infinity, right? And that's what we are having here also. Just look at this. This whole thing is I of infinity and this is I of 1. Like literally, how cool is that? So this becomes I of infinity minus I of 1 equals pi squared over 16 minus I of infinity minus I of 1. Okay, and yeah, and then, oh, let me just check that everything is correct. Wait a second, wait a second, wait a second. Uh, oh, I think I messed up somewhere. Oh, okay. I did notice that. Look, there was already a negative sign outside this big integral. So if we just write it like this, so you have to change this from this sign. We have to change the sign of this one also. So we are going to have a positive here. Like I'm talking about here only, guys. So I'm sorry about that. I didn't notice that. So yeah, this is I of 1. Okay, and now you can see that um, okay, so yeah, now you can see that this becomes 2 times I of infinity, and okay, and minus, oh wait a second, minus pi squared over 16 equals 2 times I of 1. And please remember that I of 1 was I, and I of infinity was pi squared over 12. Let me just check that again. Where's that? Yeah, here it is. So yeah, okay, let's just plug these things inside our result. So 2 times pi squared over 12 minus pi squared over 16 equals 2 times I, right? So that's gonna give us pi squared over 6 minus pi squared over 16 equals 2 times I. That says 2I equals, when you solve this, so you have to take 16. So this comes out to be 96, and then um, 16, I think. Yeah, I'm going correctly. Wait a second. So yeah, I just figured this out. I took some seconds only. So this is sorry, 16 pi squared and minus 5 pi, oh I'm sorry, 16 minus 6, 16 pi square minus 6 pi squared. So 2I equals 10 pi squared over 96, and hence I comes out to be 5 pi squared over 96. And this is the value of the Ahmed's integral. Like, isn't that really much amazing, guys? That is really much amazing, I think. Yeah, here it is. Like, this is how amazing this is. And this, the result equals 5 pi squared over 96. Just have a look at this crazy looking integral and the result. And the work we did is, yeah, it's quite good. It was quite like heavy integral, I think, because we took almost 4.55 pages of like this tablet. So yeah, that's all, guys, and thank you so much for watching this video. And if you have watched this video till the end, I hope you got to know, you got to learn something from this. And if you got to have, please please consider hitting the like button, and if you can, then please subscribe to the Quantum Mathematics. Stay tuned for the next video. Thank you so much. Just keep supporting me. Love you guys. Goodbye.